Hello, everyone, and thank you for joining us. My name is Max Odkins. I'm an environmental scientist with the Fire and Resource Assessment Program here at CAL FIRE, and I'm excited to have you here today for this presentation in our Forest Health Research Program Grantee webinar series. Today, we are joined by Drs. Andrea Duane and Hugh Safford from the University of California, Davis for this presentation, From Past to Present, Revised Estimates of Historical Burned Areas and Emissions in California and Modern Deviations from Pre-Euro-American Settlement Fire Frequencies. Before we get started, we do have some quick housekeeping. So this presentation is being recorded and it will be posted to our webpage. You can find the recording for this presentation in the future, as well as some of our past webinars that we've held, recorded and posted on that same webpage. You can use the QR code to find where we have the recordings of all of our previous webinars. And we will have a Q&A session at the end of the presentation today. So at any point during the presentation, you can go ahead and use the raise hand feature or enter your questions in the chat, and we'll get to them after the presentations. Today's presentation is part of CAL FIRE's Forest Health Research Grant Program, which is funded in part by California Climate Investments, which puts cap and trade dollars to work in communities throughout California. Our program aims to prioritize and fund research in forest health and fire science critical to the state of California, share the scientific information that's produced from that research, and support statewide plans, including the California Wildfire and Forest Resilience Action Plan. Without any further ado, I am very happy to introduce our presenters today. Andrea Duane is a postdoctoral researcher at the University of California, Davis, focused on understanding and quantifying fire regime changes at landscape scales and their effects on ecosystems. And Hugh Safford is a fire and vegetation ecologist at the University of California, Davis. With that, I will turn it over to you. Thank you so much for being here and presenting your research.
Thanks for having us. And actually, I would like to note that as a little bit of an advertisement, there is another interesting webinar. I'm obviously including our webinar in the category of interesting before it starts. You can opine on that at the end. But at 3:30, Sean Parks from the Aldo Leopold Wilderness Research Institute will be giving one of our FERO lectures at UC Davis, and that is being cast through the California Fire Science Consortium. So you can spend the whole afternoon on webinars. Any rate, great. So Andrea, I guess I'll take the beginning and then you'll jump in. Okay.
Can you see my screen?
I can see it, thanks. Yeah, and
okay.
I'll just tell you when to move it forward. So I want to note that this is the product of an agreement that we have from CAL FIRE that actually was a bit of a Frankenstein. There were 2 or 3 different projects that we'd been talking about pulling off 3 years back, and this all got kind of pulled into the same box. We're not going to be talking about all of the components of the project, but rather we'll be focused on historical burned areas and emissions and some of the work that we've been doing with revising the fire return interval departure data set and database in California. So anyway, in terms of some introduction to the topics we'll be talking about today, as you know, California fire regimes are changing. They're changing at an increasingly rapid rate, and this is leading to risky conditions for humans on a lot of the landscape, but also to some pretty serious ecosystem degradation. And among those issues are increasing smoke emissions from some of these huge wildfires that we're having. There are a lot of ecosystem impacts from changing fire regimes. There's too little fire in montane forests. Believe it or not, there still is too little fire in a lot of our montane forests, but there's too much fire in a lot of Southern California, near a lot of urban areas, and in sagebrush and pinyon ecosystems in the Great Basin. And conifer forests across the state are having a hell of a time recovering from a lot of these large and severe fires. Next slide, please. So when we think about how we are going to respond to these phenomena as scientists and as managers who use science in their management, we have to think about temporal trends, right? I mean, you can't understand directional change unless you know what the starting point was or have a decent idea of where it was. And we need some idea of reference or baseline conditions to be able to understand, as I just noted, the direction of change, but also its magnitude. We also need those to be able to understand what the actual proper context is to understand current conditions. And we'll be talking about a little bit of that here during our presentation. for some phenomena, historical conditions, baseline conditions, some reference condition state may provide a glimpse into what we might call resilient or sustainable conditions. And this, of course, is one of the basic tenets behind the science of restoration ecology, right? That there is some past state that we can identify often through things like paleo data or historical archaeology or whatever, in which ecosystems tended to function in a more resilient fashion. Is there some way that we can get back to that state? In other ecosystems, some kind of return to the past may actually be a necessary first step toward preparing for the future. And I've called this, using history as a waypoint rather than an endpoint. And again, we'll be talking about some of these ideas through in our presentation. Okay, next slide. So in terms of the objectives that are encompassed within the agreement that we're talking about, first of all, we are building a better estimate of historical burned area baselines in California. I should note that our co-investigators on this are Scott Stevens from UC Berkeley, Don Hankins from Chico State University, and also Frank Lake from the U.S. Forest Service. And we're essentially looking to build a better beast for historical baseline estimates based on, of course, Scott and colleagues built one that was published in 2007. And as any of you who work in fire science will know, that 18 years has been a complete game changer in terms of the availability of science related to fire and fire regimes in California. There were many things that Scott et al. Had to essentially make educated guesses at in 2005 and 6 that we have pretty good numbers on these days. Second, we wanted to use that burned area to do a new estimate of historical emissions for baseline fire regimes in the state. And also in this same vein of thinking about historical fire regimes, another part of the contract was, or the agreement was, to reformat and rebuild a little bit the fire return interval departure database, updating it from the version that we started in 2011 with respect to a number of the different input variables, and we'll be talking about that. And then finally, one thing that I won't be talking about today is we were also tasked with upgrading the post-fire spatial conifer regeneration prediction tool, which we call PostScript, that we use and the Forest Service uses to estimate post-fire conifer regeneration in California. And we'll potentially do another webinar on this a little bit later. We are in the process of writing a manuscript on our findings there right now. Okay, next one. Well, I'll cover this one, Andrea, if that's okay. So here's a little screenshot at the top of Scott's paper from 2007. This really, really important piece was, Scott will tell you, he farmed this out to a lot of journals. And 18 years ago, people didn't want to hear about indigenous peoples, the component of fire that was due to indigenous burning on the state. It felt like it was somehow non-scientific. But anyway, this paper estimated their best estimate was somewhere about 1.8 million hectares, or around 4 million acres a year in terms of total burning, and about 34 teragrams of carbon dioxide being released per year by that burning, obviously with a whole lot of interannual variability. But as I noted before, there's been a lot of new research done in the last 18 years, and some of the educated guesses that they had to make in 2005, 6, and 7 can actually be replaced with data now. We can also now, because of some of those new data, directly use fire rotation period estimates, which we need to get burned area. Scott had to use fire return interval data then to make some sort of broader and a little bit less robust estimates of some of those things. We're also now incorporating new vegetation types. Scott's original paper ignored riparian, ignored desert, and some other things in the state. And we have better products that better represent historical ecosystem distribution now in the state. Next slide. Okay, so I'm going to turn this over to Andrea now, but we'll start with talking a little bit about some of the steps that we've gone through to think about how we get better control, more robust estimates of past burned areas. And we'll start with talking about some of the historical reconstruction work that's been done of vegetation in California, and then speak more directly to how often that vegetation burned. Okay, Andrea, up to you.
Thank you for this great introduction. I'm going to go a bit more into the details of our work and the results we are having at this moment. So first of all, in order to estimate historical burnt area, we need to know two basic information. So what type of vegetation was in California, and this is always talking about the pre-European settlement, and how often this vegetation burns. So I'm going now to start with the first question here. And to do it, I'm going to tell you what products we are using and what methods we're using in order to improve this product. So we know that Scott Stephens and colleagues in 2007 used the Kukler map. The Kukler map is a map that was done for the whole US, but it was hand-drawn without a defined methodology, and it doesn't include like some disturbances, and the vegetation typic was idiosyncratic. So we are using another product, a very well-known product by most of you, I guess, which is the VPS, the Biophysical Settings from the program Landfire. The VPS represents models of pre-European settlement, fire, and successional dynamics, and incorporates growth and fire. In California, there are like 164 vegetation types from the VPS, and we've been doing a work of crosswalking these types into 35 pre-settlement fire regime types, which at the end are categorizations of vegetations with similar characteristics in terms of fire regimes. 28 of them were coming from the Van der Water and Safford 2011 paper, and we added the new PFRs to more like grasslands and desert vegetation. But as most of you know, what happens is that although the fire return interval is based on pre-European settlement fire regimes, the map, the actual map of BPS, is modeled based on modern plots of data. And current vegetation is already perturbed in regard to historical vegetation. So here we see that there's an underprediction of grasslands and other herbaceous and vegetation cover in California, where pre-European population was high. So what I'm going to do now is, in the following slides, I'm going to tell you how we are overlapping some new evidence and information we have about historical distributions of grasslands in California. So at the end, we are using this VPS as a base map for California, and then we are putting new information basically according to 3 different sources. The first one is very well reconstructed products of the vegetation in the Central Valley, especially 3 products which integrates various sources like even Kukler map, historical landscape descriptions, soil surveys, irrigation maps, and so on, to reconstruct what all these projects call the pre-European settlement vegetation map, habitats, or even like pre-19th century map. These 3 products are the Tulare Basin map, done by the Stanislaw Endangered Species Recovery Program at California State University, the Sacramento-San Joaquin Delta historical map done by the San Francisco Estuary Institute in 2012, and the Central Valley Historical Mapping Project from the California State University in Chico in 2003. So in this order of prioritization, we are putting this information in the map, in the VPS map, in order to be able to account for all these like very specific efforts that we have in all these areas that do a very good reconstruction of historical vegetation. Then we are also including some evidence we have of grassland distribution according to phytoliths. Phytoliths are microscopic structures of biogenic silica, and vegetation composition is the dominant driver of soil phytolith content. It's considered that when you have more than 0.3% of soil phytolith content, you can assume that native grasses were there dominating the landscape for centuria or even millennia. Fick and Evet in 2018 provided a map of phytolith density across California according to more than 100 plots in which were sampled the phytolith density. So if we use this map, we can see at the map in the right that the places where we had more than 0.3% of phytolith were mostly, we can assume that they were mostly dominated by grasslands. It's true that we are using the presence of these phytoliths as true presence of grasslands. We are not using the absence of phytoliths as absence of grasslands, because other types of portlands, for instance, can be dominating the landscape, that then they don't leave the same amount of phytolith than other type of grasslands in the landscape, in the soils. Finally, the third big modification we are doing to the VPS map is taking into account pre-European settlement, indigenous population and management. So prior to the American settlement, Native Americans exerted a profound influence on vegetation through much of the state. Active vegetation management was most intense in areas with the highest density of people, in particular near villages and trails. To account for this, we are using a method in which we identify which pixels we will convert to early several stages of vegetation based on locations of high population density and intense human land use. So the map on the left, it's what we consider a good representation of the historical and native groups in California. And this zoom here is a quite well-known map of the Patwin area done by Crover 1932, in which he maps a lot of villages' location. So this is just an example, but in our work, we've been digitizing dozens of maps, especially from the Handbook of North American Indians of the Smithsonian Institution, but also from other sources. And for each of these maps, we've been locating all these different villages. And also we've been doing the same exercise for the main trails. These are, of course, the main trails, the trade trails in California. So as sources, we have 6 sources of very extensive reports for some of the tribal groups, like the McLellan and Johnson 1999 for the Chumash, Kroger 1932 for Patwin and Noblaki, Hazer for Shasta, and so on. When we have these ones, we fill the rest of the areas with the Handbook of North American Indians, Volume 8 of the Smithsonian Institution, wherever they have maps. And we also use the Atlas of Western Prehistory of Wilson and Wilson 2022 to fill other gaps. So we end up with this map that you see in the right of villages location in California, in which we have like more than 2,000 villages that, according to the discussions we are having from experts, it's certainly an underestimate, and more than 14,000 of trails, which is like almost 9,000 miles of trails. But after our discussions, we're thinking like we might be missing part of the story, because here I'm just bringing an example of 2 areas of similar size, not too very far away from each other, and map from the same source, which is the Handbook of North American Indians. In the one on the left, you can see that for an area of 85,000 hectares, we have like more than 85 villages, which makes 1 village for 10 square kilometers. And for a similar area, not too far away, the same map, and the same source, we have only 19 villages, which makes us think that the effort on mapping the historical village was not the same. So we might be missing some of the locations of these villages, and that will have an important impact on our results. So at this moment, our approach is, what if we try to have likely estimates of villages location? And at this moment, we are using an AI approach based on vegetation, digital elevation models, and ecoregions to reach similar densities. Unfortunately, I cannot show you results today, but of course, when we have the final results of the project, you can consult it or even just email us. But the idea is not like reaching like where villages were exactly, but trying to get estimates that are more according to the good sources of information we have. So once we have the village locations, what we are doing is assuming that all the vegetation surrounding these villages was intensely managed by the population. So we are actually we've been applying 2 different buffer sizes, like 4 kilometers and 8 kilometers, which we can like 5 miles. And we are applying in these areas of active management rules for like converting to farm maintained grassland types. This is applied only to certain vegetation types. So there's these rules, like only to shrubs, mixed evergreen. So the types that we assume that are coming from encroachment of these grasslands. And we are also applying some topographical rules, for instance, not occurring in lower slopes or bottom valleys, and having different vegetation types according to a combination of slope and aspect, as it was proposed by this paper of Greenler and colleagues in 2024. And also we are assigning a new vegetation type according to the distance to the coast, to the elevation, to the precipitation, and so on. So once we put all this information together, I'm sure that you think that that's a lot, but we have everything like in code, and we can just track all our decisions. We can have like a new proposal of a map in California, and this is I'm showing is the Cookler map on the left, the original VPS, but with our PFR type, the 35 PFR types, and the present study with the 8-kilometer buffer around the villages. The brownish colors are like shrublands, and dark brown is chaparral. What you see in like light green, it's more like grasses. The light blue is like oak woodlands. Blue, like more strong blue, is like marsh ecosystems, and then you have all this range of greens, even red, yellow, and pink to map all these different forest types. So you can see, I'm sure you can see already some substantial differences, like especially between the VPS and the methods derived from the present study, especially in Southern California, where the PPS is mapping mostly coastal sage scrub, but with the present methodology, we are reaching all these coastal prairie areas around the coast. And you can also see a lot of differences, I'm sure, in the Central Valley in California, and even in the Central Coast. And if we zoom a little bit, this is the Karug area, which is northern Eureka, and the picture in the left is the VPS map, mapping all these redwoods and mixed evergreen. And in our methodology, we end up with a map like this, in which you see a very interesting mosaic of grasses or woodlands and mixed evergreen, having taken into account also topographical characteristics. And also zooming in another area, you can see in the left the VPS as this map, and in the right our map, in which you can see much more like coastal prairie, less chaparral, and less mixed evergreen, and also a lot of oak woodland in the left part of the image. That's for the Chumash area. And if we look at some numbers, this table is in the edge of the row is a different ecoregion in California. The last one is for the total California. And in the columns, you see grasslands, shrublands, and forest. And within each of the columns, you see like the historical, both for the VPS, original VPS, and our map. And also we are adding here the current distribution according to FBET, just to have an idea of what's going on. And if we look at some of the values, for instance, for grasslands, we see that in central Western California, which is mostly the coast, the grasslands with our map increased from 38% to 57% from our map, which is much more similar to what we currently know. I mean, grasslands here is also including oak woodlands, because it's the type of vegetation that burns is more the grasses. So it's kind of maybe a different classification of what you're using in terms of oak woodland, but these are considered here. Southwestern California also sees like from a 6% of grasslands up to 51%. And of course, there's much less now because of the anthropic land uses like urban areas or agriculture. In terms of shrublands, in the Central Valley, there's a strong decrease on the shrubland type from the VPS to our map. And for instance, the forests don't change that much. In the Sierra Nevada, you can see that we're still having like 57% steady in the VPS, our map, current vegetation. So now that we have a product that we still know that we need to improve it, but it's kind of what we believe it's a good and robust approach. We need to know how often did the vegetation burn. And to do it, the best and most, I think, known method is to using forest garden chronology. That's mostly for woodland vegetation. But we can also use a bunch of other information coming from sediment cores or even oral stories and writings for other vegetation, non-woody vegetation types of grasslands, or even riparian vegetation or desert vegetation. So in this work, in this project, we've been like putting together all this information in order to get new estimates of fire return intervals and fire rotation periods. So what's actually this? So the fire return interval is easy to understand. It's the number of years between fires. And it's like, I mean, this specific site burns every 15 years or every 20 years, and it's kind of easy to understand. But what's the fire rotation? Most of you might know it, but the fire rotation it's considered the number of years needed to burn a region of interest, and it actually takes into account the spatial components. So it's like the burned area and the frequency. And it's calculated by having a region of interest and you divided by the burned area per year. And if you do a simple conversion, if you want to get the average burned area per year, you need to divide your region, like your vegetation type surface, by its fire rotation, and then you get the average amount of area burned per year for that vegetation type. And after like looking out there in the literature and talking to a lot of experts, this is the values that we are getting in this work for 19 vegetation types. This has been like the fire rotations that directly pulled from the literature, and for the other ones we are using some kind of surrogate coming from the fire return interval because it's not always easy to get the fire rotation periods. So we are also using fire return interval as a surrogate. And just to have a zoom of some of the values, we have like kind of low fire rotation periods for grassy vegetation like California grassland, coastal prairie, or marsh ecosystems. Also for vegetation as dry mixed conifer, and we have medium levels for chaparral alternate conifer, 7 years, and then we have like much higher values. That's the best information we have for lowland coastal riparian or alpine vegetation. And these are some of the results we have when we apply these fire rotations to the historical map that I showed you before. We want to really highlight that those are provisional results. We think that once we get our village mapping work done, we will have like different values, but we wanted to share our first attempts with you. You can see in the plot on the left, there are like 5 columns. Let's say this is the present study, Scott Stephens study, Martin Saps in 1992, and their estimates in terms of historical burnt area for forest, shrublands, and grasslands. And also the 2 last categories are the mean actual burnt area in California in between 1980 and 2023, and the maximum. So as you can see, we are having like lower values than our colleagues' studies, mostly for grasslands. And well, we need to still working and figure out if this is specifically because the fire rotations or the mapping efforts. And we are also discussing this in our group of authors, but the forests are more or less in the same range of values, and shrublands are also a bit lower. If we see this, the plot on the right, this is for the different rows are the ecoregions in California, and in the columns are different because we didn't like only apply the different mapping like 4 kilometers or 8 kilometers, but also different values of fire rotation estimation, so low, mean, and high, because we wanted to have kind of a fork, kind of an uncertainty, because we know that we are providing estimates and we need to provide a range of values. So this is like from the lowest to the highest, and you can see that the greatest burnt area is mostly in the Great Valley when we have like short fire rotations, like the lower estimates of the fire rotations. And this plot compares the actual burn area in California for the last 43 years with our provisional estimates. And this is specifically for our very lowest estimate. So the horizontal line is the estimate we are calculating in this work. The orange is shrublands, dark green is forest, and light green is grasslands. And you can see that we've reached several times the provisional estimate of historical shrubland mean burnt area, up to 4 times the forest area, and almost never mostly never the amount of grasses that were burned before European settlement. So now I'm going to talk about the third part of this work. Well, not the last one, but third in terms of, okay, we know what California looked like, how often it burned, and what were the associated emissions from these fires. To do it, we are using a modern simulator, is FOFEM. FOFEM was used also by Scott Stephens and colleague in 2007, and it's also used by CARB in order to estimate emissions from current fires. So we thought it was a good idea to use the same method. And to do it, you need to know what vegetation type burned and the surface burn. So that's what I just talked about. You also need to have some field loadings and the weather conditions in which they occurred, because California before the European settlements was known to be influenced by the Little Ice Age. And just as an example here, this is the reconstructed climate in California for the Palmer Drought Index for June, July, August, in this period of time between 1500 and 1800. And you can see it's mostly like white or light blue. So the conditions at that time were not as harsh as they are right now. So we need also to take this into account. So in order for the field loading, what we are doing is we are getting the last FOFEM database in which they propose different field loadings for different vegetation types. They have different classification systems, the FCCS, NVCS, and the SAF-SIRM. So what we are doing is we're doing a quite complete crosswalk with our PFRs, our vegetation classification, including if we have more than one source of information. So we end up having one average field loading for each of the PFRs, plus the standard deviation, and that would also help with uncertainty measurements. And we are assigning one FOFEM is called the light field loads, which we consider that in that time, because fires were more recurrent, the field loadings in the vegetation were like in the light part of the range. Also for serpentine types, we have modifying these proposed values according to the Siervo and colleagues 2015 results, in which they demonstrate that the field load and serpentine types are lower than the same vegetation type, non-serpentine. We also need to include a percentage current consumed, and this is done according to the values of historical high severity and moderate severity fire in VPS. And we have these values here, and for instance, you have that in chaparral serratinous species, 65% of the crown was consumed, and in other types, we don't put a 0 because it's almost never a 0, but like the lowest value is like 5% of the crown was consumed. That's important also to have the emissions part. In terms of weather conditions, as I was saying before, we are using the same approach as Scott Stephens in 2007, because at this moment we also are aiming at providing similar methods to compare our results. So 1/3 of the burnt area was in summer under very dry conditions, and 2/3 were in fall under dry conditions. We are not including it here, but we also plan to include a sensitivity analysis to know how the results are changing according to these changes in weather conditions. And we are also using a Monte Carlo methodology in order to have uncertainty around the field loading estimation. We are running more than 1,000 FOFEM simulations using these different field loadings. What are our results? As I'm saying, those are provisional results because everything is based on the mapping and the fabrications, but we also want to share with you what we are reaching at this point. This plot shows for different smoke components, the methane, nitrous oxide, particulate matter 10 microns and 2.5 microns, different total gigagrams emitted annually for each vegetation type. Basically, you can see in yellow colors highlighted the ones that provide like largest amounts of fine particulate matters, which is the combination actually of the field loading and the fire frequency. So, and the fire in the vegetation area. So dry mixed conifer, mixed evergreen, moist mixed conifer, redwoods, and yellow pines are the one more contributing to the smoke's emissions. And surprisingly, California grasslands, even was the largest surface, was not contributing almost at all in these smoke emissions. If we look at carbon monoxide and dioxide, we have like kind of similar results in which this is another scale, because you can see total gigagrams is almost 10,000, so it's like 10 millions of metric tons, but this is for dry mixed conifer, mixed evergreen, moist mixed conifer. They are the ones providing the highest carbon emissions, but here grasslands is not zero. It's also contributing to the total emissions to a kind of a more highest level than the previous plot. If we compare to Scott Stephens' 2007 paper, in this case, we are using lower estimates in both cases. We are finding that consistently we are finding values that are more or less in the same scale, but at consistently lower levels than his results. And if we look at the average per acre burned, for like our average estimate, Scott Stephens was finding that 7.5 metric tons per acre were emitted in their fires. In our estimates, we are finding 6.73, which is kind of similar, a bit lower, mostly because differences in field loadings and ground consume. But the important thing here is they're really different from modern fires. Modern fires, the average is 24 metric tons per acre burned. If we do the exercise of mapping this, we also see some differences. So this is the same information I was just showing you now in the slide before, like mean carbon emissions per acre burned, but according to a different California air districts. To do this exercise, you need to understand that we assume an equal spatial probability of burning across all pixels. So we don't know where fires were occurring every year. We just did apply the probability of having a fire equally across all the pixels in that vegetation site. And even we were finding that the average is 6.7 metric tons of carbon dioxide per acre. This has differences according if you are more like in the northwestern part of California, central part of California, or southern part of California, especially related to field loading in each of these areas. If we apply the same, but in each air district, so we are doing the total emissions in each air district, this has kind of a different shape, but it also has to do with the surface of the air district. So if you are larger, you have more chances to have more total contribution to the carbon dioxide emissions, even though in places like the Mojave Desert, these areas are still having like low contribution to the total carbon emissions here. And you can also like divide this according to the whole district surface. So you have an average kilos of carbon dioxide emitted per acre, total acres in that region. So it could be kind of a measure of exposure. And the north and northwestern part had a higher carbon emitted, average carbon emitted per that region than central or southern California. And now for the last part of this presentation, this is kind of another story, I mean, related, but it's just like another section. We are, as Hugh was mentioning at the beginning of the presentation, we are providing new estimates of FRID in California. So this is an actual modern deviation of fire regimes according to historical fire regimes. Safford and Vandenbach in 2014, they proposed this metric, which is the fire return interval departure, in which if you, per each pixel with its vegetation type, you calculate the current fire return interval, and you calculate the difference between the historical fire return interval, and you make this as a percentage, and you can get like from minus 100 to 0 and towards 100 how departure you are to the historical fire regime. In this plot over here, the blue colors mean that you are having a fire deficit, so missed fire cycles, so you're having less fires currently than historically. And for the warm colors like yellowish and orange, you're having excessive fire of this currently according to, regarding the historical fire return interval. So this work was done in 2014. It's been very useful. A lot of people use it in kind of their prioritization methods. It's used by managers, but it has some limitations here in California, which is mostly that it was applied to federal lands. It was not covering all vegetation types at that moment. And its base map is the 2011 CalVeg or eVeg map. So there are some potential improvements here, like update fire return intervals for all vegetation maps, use FVeg for current vegetation across the whole state, also use a new historical map of potential vegetation, the one I showed you at the beginning. And also, I'm not going to show any results here, but we can even include an uncertainty measure. So how is this departure statistically significant departure? Are we having enough fires to confirm that this is departure? We are working this with other colleagues, and that's going to be like applied at the whole US state. So this is going to also to be in this project, but I'm not going to show any results at this moment. The slide I'm showing here is the application of the new FVeg, of the new FRID map according to all California lands, using on the left map, you see eVeg or CalVeg plus FVeg. So we are merging these two sources in order to have this new map. We are using fires up to date, so from 1908 until 2023, and the fire return intervals are using the Vandenwater plus the land fire ones that are proposed. And the right map, it's exactly the same, but instead of using the eVeg plus FVeg, we are using the new historical map that I was showing you 10 minutes before. So it's kind of what was California like before the European settlement. Of course, we have included in this area like anthropic areas like agriculture and urban areas, because we think it doesn't make sense to say that we have a departure in these areas. And even the historical map is showing another land cover. If we zoom a little bit, we can see that the small map that just popped up, it's the one from Safford and Vandenwater 2014. So we are showing new results for the northern central coast, in which we see that actually we have a bit too much fire in some parts of these coastal ranges. Some parts of the northwestern parts of California are turning a bit more light blue, which are like shrinking these deviations from historical fire regimes. But in some parts of Southern California, we are seeing even like more red color. So we are having excessive fires in many places in Southern California. But what happens if we use the historical map? So instead of applying the fire return interval to the existing vegetation right now, what happens if we apply current fire return intervals to what's supposed that was happening before the European settlement? So we have kind of a change of colors here. Everything turns even more bluish. So we don't have that excessive departure in Southern California, and so it's not excessive fire, but we are having actually in many places like not that amount of fire that the grasslands were burning before the European settlement. And in many places in the central coast and northwestern coast, we are still having like this dark blue. So we're having less fire than expected. So this is an exercise more to discuss what could be like the appropriate fire regime for each of these places. Finishing today, takeaway messages. Reproducing historical fire regimes is challenging, but recent data and methods advances provide better estimates. Historical fire regime reconstruction can quantitatively incorporate indigenous cultural burning in the estimation of vegetation type distribution and fire regimes. Our provisional results mechanistically account for indigenous burning, which increases the grassland type cover, and this increase expands the total burnt area and decreases total emissions. The recent wave of large fires is shrinking the positive fire return the FRID departures, so the FR return interval departures in some Northern California forests, but Southern California is seeing increasingly negative departures, so it's still too much fire in some parts. And of course, different historical vegetation maps show different patterns that can help the discussion. We, of course, want to acknowledge all of the co-authors and collaborators in this project, which have been like really putting time and ideas for the discussion we just presented today, Hugh and I. And that's all. We are happy to receive questions and ideas, or even like, hey, I have this historical map, why you are not using it? And we are super happy to hear about your feedback on this. Thanks.
Fantastic. Thank you so much. We're going to switch to question and answer in just a moment here, but before that, I'd like to take a moment to thank our presenters one more time. Thank you so much for being here and for sharing this work that you're doing with us.
Thanks for the opportunity.
Thanks.